In this lecture, you can see we're calculating volumes again. We're using a method called the washer method, which is related to but slightly different than the disk method. And it has to do with the type of shape that's being revolved around either the x-axis, the y-axis, or a horizontal line or a vertical line. The shape causes us to get a different type of disk, if you will. We actually get a washer. So our first problem is to find the volume of the solid formed by revolving the region bounded by the graphs of f of x equal x plus 2, which is, of course, a straight line, g of x equal x, which, of course, is a straight line, the vertical line x equals 0, and the vertical line x equals 3, and we're going to rotate that about the x-axis. So let's see what the graph of this region is that we're going to rotate. Okay, we see a sketch of this region. This top line right here is y equal x plus 2, or f of x equal x plus 2. And this bottom diagonal line that we see here is g of x equal x, or y equal x. X equals 0, of course, is the vertical line over here on the y-axis. And x equals 3, of course, is the vertical line that is at the right end of this shape. So we're going to rotate that about the x-axis. And we approach this as we did before. If we're rotating about the x-axis, we want to think about a rectangle oriented in a vertical position that is perpendicular to the x-axis. And of course, that's going to be an infinitely narrow rectangle. And since that rectangle's narrowness, or width, if you will, is based on a direction of the x-axis, we call that width dx. Now, we have a little bit of a different issue here, is that if we want to find the height of this rectangle, that's based on the top line and the bottom line. And so this height of this rectangle, this dimension of the rectangle, would be f of x minus g of x, which in this case is always 2 units, isn't it? Isn't that 2? Because f of x is x plus 2, and g of x is just x, and so that result is 2. And of course that makes sense. Those lines are always 2 units apart, so that does make a little bit of sense. Well, let's see if I can draw the shape that this rotation is going to cause. So let's see here. That's what the shape is going to look like. Okay, I think we would have some shape like this. You see that this space that we see out here, right in this area, has to do with the edge that we see right there. And of course, that's not creating a solid, because as that rotates, there's leaving that gap in the middle. My perspective may not be real good, but I've tried to draw something that kind of shows us that idea. So this is kind of not quite a cone on the outside, but a cone that is empty on the inside, you see. So it's not a solid. It has kind of a open space in the middle. Now, let's imagine what would happen when we take this strip and it rotates. It's also going to leave a hole in the middle. Let me see if I can kind of show the shape that will create. Okay, so as we rotate this shape, that's kind of the piece that we see over there to the left, and that's being rotated, and so it sweeps out the kind of the outer edge, but that still will have a hole in it, and that hole is based on this part that's missing right there. Okay, so you see, that's why this is called the washer method, because the shape that strip creates as we rotate about the x-axis looks like a washer. Okay, so we're going to find the volume of the entire solid by finding the volume of a single washer that is infinitely narrow, and we're going to add up the volumes of all those washers, the infinite number of those, using integration to find the volume of the entire solid. So let's concentrate on this washer. Let's draw the washer here. Okay, here's our washer. Now the height of this washer is the dx. Okay, remember we laid the washer down on its side. Now we can think of the washer without the hole, which would be a disc. And then we can think of the hole itself, which is an imaginary disc. In other words, there's two radii, if you will, that are at play here. And one of the radii, one of the radiuses, is from the center of this washer clear out to the outside edge. Okay. Now, that outside edge is defined by the top curve. See, it's the top of that rectangle that we rotated. That's that outside edge. And let's call generally that radius capital R, and in this case, it's the top function, f of x. Now, there's also, if you will, the radius of the hole. Okay? And that radius is defined by the bottom of our strip. Now, let's call that radius lowercase r, and in this case, it's defined by the bottom function g of x. I'm kind of think of that in more general terms is what I'm doing here. So we can calculate the volume of our washer. Okay, the volume of the washer is going to be equal to the volume of the disc minus the volume of the hole. So the volume of the disc is pi capital R squared times the height. Okay, so that's just, we just think of the washer without a hole in it, and we would have a short right circular cylinder, pi r squared times height, or area of base times height. And of course, in the hole, we can think of that as taking out a washer whose radius is lowercase r, so the volume of the hole is pi r squared times the same height in this case. So specifically here, let's notice that we have a pi and an h that are common factors to both of these. Let me factor out the pi to the front and the h to the right, and so what's left is capital R squared minus lowercase r squared. And in this particular case, I could be very specific, but I really want to point out that the capital R squared is really the top function in this case, value squared, and lowercase r is the bottom function in this case, which we call g. Okay, and of course h is dx, isn't it? Now we can be very specific to this problem, but this kind of gives us the idea is the volume of the solid then in more specific terms, we'll be very, in more general terms, we'll be very specific here in a moment. will be the integral from the beginning of the washers A to the beginning, the x value where the beginning of the washer starts, A, and the x value B where the end of the end of the washers, where the x values where the washers stop. And then it would, of course, be pi times, just as we've written above, f of x squared minus g of x squared dx. And, of course, the pi can be factored to the front. Okay, well, in our problem, and I mean, that's kind of the idea, again, generally. The pi can be factored to the front. In our problem, the f of x is simply x plus 2. Oh, I guess I got a little ahead of myself up here. Really, we didn't need what I wrote up here because we need each of those pieces squared in this adaptation. So anyway, I apologize for doing that earlier. In our problem, like I said here, that the disks are going to start out an x value of 0, and they're going to stop at an x value of 3. And that's this x value of 0, and that's this x value of 3. And of course, the pi I'm going to factor to the front. Well, let's go ahead and leave it in here. In these parentheses, f of x in this case is x plus 2. So we have f of x, which is x plus 2, but that's squared, minus g of x, which is just x, but that's squared, and then dx. Now, I'll kind of leave it to you to complete here. We'll have the integral from 0 to 3. We'll factor the pi out, my bad there. And after the dust settles on the inside, what we have left here is a 4x plus 4. That is, a 4x plus 4 dx. So after we square x plus 2, and then subtract x squared, we're just left with 4x plus 4. So we're going to integrate here. We'll, of course, have the pi. And when we integrate 4x, we'll have 2x squared. And when we integrate 4, we'll have 4x. And we'll evaluate that from 0 to 3. And the result that we'll get, which you can verify, is 30 pi. And of course, that's cubic units. But the big picture is, how did we accomplish this? We created this washer. We got to figure out how to come up with the volume of a washer. And we integrate the volume of a single washer, thinking of starting those washers at one x value and stopping them at another. And we can continue. This is the thing to remember, not so much a formula, but how did we go about this process? Well, let's look at a second example of this. But this time we're going to rotate instead of about the x-axis, about the y-axis. And we'll do that on the next page. Okay, in this example, it's to find the volume of the solid formed by revolving the region bounded by y equal 2x squared, y equals 0, and x equal 2 about the y-axis. So let's draw a sketch. I'm not worried about being real accurate with my sketch, but I know that y equal x squared is a parabola, but of course we're not going to have the whole parabola because we're bounded by y equals 0 and x equal 2 also. And anyway, nevertheless here. So y equal 2x squared will be a rather steep parabola. So let's suppose this is about where 2 is for x. And then that would mean that would mean that y along the parabola would really be pretty big, wouldn't it? And so this is that parabola y equal 2x squared, and we're bounded by the line x equal 2, which is here, and y equals 0, which is here. So we're talking about this region. Okay, this is the region we're talking about. Now, it might be nice to understand what this value of y is here. In fact, I think we'll probably need that in a little bit. And of course, if x is equal to 2, then y would be 2 times 2 squared, wouldn't it? And that ends up being 8. So although this is not to scale, that value of y we know. Okay, now if we're going to rotate about the y-axis, so we're going to rotate this about the y-axis, that means the representative strip or rectangle we need to draw needs to be horizontal instead of vertical. Now, if it's horizontal, this narrow width is the width along the y-axis. So that narrow width we'll call dy. Okay? Now, we're rotating about the y-axis. What will that look like? Well, I'm not going to try to be real precise here, but let me imagine that this outside edge is going to rotate around, and when it does, then it's going to create an object. Well, let's see if I can do this. It's going to create a solid that has straight edges all the way around it. Okay, straight edge all the way around it. It's going to be flat on the bottom because our shape over here is flat. But it's going to be open. It's going to have a curvature on the inside where it's open. Let's draw and get an idea of what this might. The top, of course, is going to look like this, and it's open. But the inside isn't a parameter shape. It's more of a shape. I'm showing the inside of this. See, it's more of a shape like this. So it's kind of a flat bowl that has flat edges on the outside, flat on the bottom, but the inside is curved toward the bottom. Now, when we take this strip that we've got over here that we're talking about and it rotates, well, imagine what's going to happen. It's going to be a piece here, and let's see if I can draw this. I'm better off drawing this. Well, okay, so here's the bottom of it. Comes around like that, and this comes all the way over here. But this strip doesn't go all the way in, so what we've got, again, is a place here in the middle that's cut out. Well, that's kind of hard to see. Okay, so it's going to create a washer. This part is creating a washer. So let's imagine that washer. Now that washer is already on its side. So let's kind of draw that washer over here again, so that we have something to refer to. Okay, now of course I'm making the washer kind of big, so I have some room to work. Well, I've almost got myself in trouble. And okay, there's the washer. Now the height of this washer is dy. Okay, that's the height of the washer. And again, we have two, if you will, two radii. This big outside radius and this big outside radius. Notice that refers to, see, that's the distance, if you will, from here, from the very beginning, from the y-axis clear over to that vertical line x equal 2. See, that's that outside radius. And that before we called capital R. And in this case, that's always 2 units. See, it's straight up and down. So that outside radius is always 2 units. No matter where we are on a disk up and down here, that outside radius, which is across this direction, isn't it? Okay, is always 2 units. Now the inside radius is, of course, smaller. Well, that's a silly statement, isn't it? And that we called lowercase r. Now here's the deal about that lowercase r. That's the distance. That inside radius is the whole part. So that's the distance from here to here as an x value. As an x value. See, that's an x value, isn't it? We saw this a little bit ago. So to calculate r, okay, r is an x value, but that curve is defined as y equal to x squared. And so we need to take that and solve for x, because that's the r, the lowercase r value that we need. So we do this simply by dividing both sides by 2, so we end up with x squared is equal to y over 2. And then x would be normally plus or minus. See, it'd be plus or minus normally the square root of the y over 2. But this x that we're talking about is an x value on the right side of the y-axis. So it's the plus, not the minus. So we have x is the square root of 2. Okay. Now we have a way of calculating the volume of the washer. Okay, the volume of the washer. Remember, it's the volume of the disc without the hole minus the volume of the hole. Take that extra volume out. Well, the volume of the disk is pi times the radius of the disk, which is capital R squared, times the height, generally h. And the volume of the hole, of course, is pi times the radius of the hole, which is lowercase r, radius squared, times the height. Well, let's fill in the pieces we know here. Pi and capital R, in this case, is the constant 2. That's a little bit unusual, but it is. And of course, the height is dy. Minus pi times lowercase r, and lowercase r we discovered was just the x value, okay, the x value squared dy. But the x value, of course, is the square root of y over 2. So what does this look like? Well, in this very first position, 2 squared is 4, so we have 4 pi dy. Minus, in the second position, we have the pi. And when we square the square root of y over 2, we simply get y over 2, and of course then dy. Well, as we did a moment ago, I'm going to factor out pi to the left, and I'm going to factor out dy to the right, because those are both common factors, and so I'll have 4 in the middle left, and y over 2, for convenience sake, I'm going to write that as 1/2 y. So that's the volume of a single washer. And of course, it depends on what level of y that washer is at. That's the reason we have that variable y in there. When we move to a different level of y, we get a new volume of washer. Well, that only makes sense. So the volume of the solid here is we're going to add up all of these volumes. So it's the integral of pi times 4 minus 1/2 y dy. Remember, that's the volume of one little washer, and so we're adding up all of those volumes to get the total volume of the solid. But now we've got to start and think where these washers start. Well, we're moving these washers from low to high. See, we're moving the washers in this direction. So the very lowest washer would be at a y value of 0. That's important to recognize that we're talking about y values. Of course, that kind of corresponds with this dy and this y, doesn't it? And then the very top washer is going to happen when y is equal to 8. That's as high as y can go. So our integral then becomes, factor out that pi, the integral from 0 to 8 of 4 minus 1/2 y dy. Well, when we integrate 4, of course, with respect to y, we get 4y. When we integrate 1/2 minus, when we integrate 1/2 y, we will get 1/4 y squared. And of course, we're evaluating that from 0 to 8. I'm going to let you fill in the details here, but you should get 16 pi as the final result. Of course, 16 pi cubic units. Well, that certainly ought to get you started in all of your homework, so I'm going to leave that to you, and we'll meet again in the next lecture. Good luck.